Okay. You are at the mercy of our internet supply. Uh, um, just make sure that you watch the lesson or study it yourself. Today's goal 8.1, no, sorry, 8.2 and 9, chapter 9. Okay, here we go. Now, here's the thing. Chapter 9, okay, in case you don't know, chapter 9 is the most important lesson in all of AP Stats. Because if you don't know chapter 9, like you're done. Like nothing makes sense to you, okay? So today what I'm trying to do is break down, okay, finish 8.2 as quick as I can, okay? Make sure everybody here understands. Once 8.2 is done, okay, chapter 9 technically should be started at the beginning of January. In the past, I usually skip chapter 8. Like I'll just tell people, go home, watch it, this and that, okay? This year decided not to, okay? So right now, we need to finish chapter 9. If we finish chapter 9 by today, then you guys are going to be doing well, okay? We're talking about everybody here, okay? Yeah, if we don't finish chapter 9, you're getting, okay? Okay, make sense? All right, here we go. Chapter 8.2. Let's get this done. Online stats notes. Okay, here we go. Is this it? Okay, let's do this. Okay, I randomized the group, so you guys do it yourselves. What do you guys want? Huh? Okay, just get it done no matter what. Okay, all right, here we go. Lydia showing up. Okay, now, okay. So there's two types of distributions. Okay, we looked at. Okay, first one was binomial. Okay, binomial outcomes are always going to be binary. Okay, yes, no, black, white, up and down, whatever. Okay, and then there is a finite number of attempts you have. You go to the free throw line. David wants to shoot free throws. I'm just checking I'm recording this too. Okay, hold on a sec. David wants to shoot free throws. And then let me check. Okay, it is recording. Okay, again. Okay. And then the question would be like, hey, he took 1,000 shots. Okay. What's the probability that he'll make between like 100 to 200 shots? Okay. That is for binomial distribution. Today we're doing something different. This is called geometric distribution. Now, the main thing is the difference between binomial and geometric is the purpose is different. Geometric is how many shots does he need to take until he gets his first one? First one, okay? So let's say if David goes to the free throw line, okay? Takes the ball, okay? Throws it, okay? And he airballs it, okay? First attempt, okay? Okay, tries again, takes another ball. Okay, by the way, let's say his free throw percentage, probability of getting in, is 0.000001, okay? Second shot, okay, hits it, okay, over the basket. Okay, that's 2 attempts. Third attempt, 3 attempts, 4 attempts. Keeps on doing this, and he basically misses a whole bunch of them, okay? So the number of attempts theoretically could be what? Infinite, okay? So make sure you remember this, okay? For geometric, the main difference is the number of attempts could be infinite, okay? Different from binomial. Because for binomial, there must be what again? Fixed number of outcomes, okay? But for geometric, you can have infinite number of outcomes. And the second main difference is, what's the purpose of geometric again? Yes. How many tries do you need until you get the first success? That's what geometric is all about. Make sense, everybody? Okay, here we go. Okay. Oh, by the way, this was a game that we play called Stocks. Okay. But here's the thing. Why don't we skip the game today? Because this is the time restraint. We'll come back and after the assessment week, we'll play this game one time. Everybody okay? And then we'll play this game. You want to play for candy or any kind of food or bonus marks? What do you guys want? Bonus marks. Oh, all right. All right. So if you lose bonus marks. How's that? Okay. If you win, you gain some. Okay. Yes or no? Okay. Anyhow, okay, we'll skip this. Okay. Anyway, I'm moving from geometric distribution. Here we go. Geometric distribution is a probability distribution, meaning like this term over here, probability distribution, just means how the graph looks like. If it's normally distributed, it'll be like a bell-shaped curve. If it's binomial, depending on how many outcomes, you also could have a bell-shaped curve as well, okay? Or it could be skewed, okay? Now for geometric, the probability distribution describes the number of trials that you need until you get your first success. Okay, everybody? Now, how do you know when you can use a geometric? Condition number one, your outcomes must also be binary, meaning it could be fail or success, okay? Fail, 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 fail. And then your last one is a success, okay? So how many fails do you need until you reach your first success, okay? It's like life. How many times do you need to do something until you get your first, success? Okay. How many times does so-and-so need to ask? Okay, until he gets his first yes. Okay. Okay. It's okay. It's okay. Bowen know how's it feel. Okay. Okay. Bowen can talk to you all about it. Okay. I was like, no, 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 no. And then finally, yes. Okay. Yeah. In case you don't know what we're talking about, don't worry about it. Okay. Okay. As long as nobody is missing action. Okay. 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 Number one. Okay. Outcomes must be again binary. Okay. Here we go. Number two, independent trials. Okay. What this means is the probability of success for every single trial must be independent of each other. Okay. If you're talking about drawing a card, you take a card, it's a fail, and what do you get? You always put it back. Okay, so far? Right? And the way we try to see this is whenever you're dealing with geometric, it's like, here is the pool of everybody. Okay? Everybody in this box. Okay? And inside this circle, okay, are the people who would say what? Yes. Okay, so these are all the yes. Okay, you ask any of them, they all say yes. But outside are all the people who would say no. Okay, and what you're really doing is you randomly pick one person every single time. Like meeny, meeny, money. Okay, this one. Oh no. Okay, put it back in. Shake it up. Next person. Okay. Oh no. Again. Okay, put it back in. Shake it up. That's how the process works. Okay, every single trial is independent of each other because if one person says no, you throw back in, and then you wait for the next one. Or even the same one, whatever in the pool, and you pick the next one. Okay? Make sense, everybody? Okay, here we go. Outcome of each trial should not be affect each other. Okay? All right. So one complaint about the basketball example was someone would say, hold on a sec. Every time you took a shot, if you know you missed, it didn't work, aren't you gonna improve your shot? That is true for most people. Some people never learn. Okay? It's young. Okay, it didn't go in. Okay. You get the point? So every single one is independent of each other. Constant probability of success. Okay. The probability of success for every single trial must always be the same. Okay. How many is that? 1, 2, and 3. Okay. And then the last P must be constant. And the last one is the number of trials is not fixed. It could basically become infinity. Okay. So 1, 2, 3, 4. Anybody check with your partner or someone next to you? Ask him, are they okay? Do you understand this? Do you have any questions? Okay, ask him right now, please go. Are you zoned out? Yes. Okay, ask him, do you understand? Are you worried about university right now? Okay, don't. Okay, how many universities do you apply until you get your first success? Okay, Mr. Young was 1. I got him right away. Okay. Okay, hopefully that's the case. Okay. All right, next. Oh, okay, here we go. Everybody good? Okay, couple other things. When you look at, couple things. When you're looking at the distribution of a geometric, okay, I want to ask you, what do you think the distribution looks like? Skew left, skew right, normally distributed. What do you guys think? Okay, so let's say, okay, which side is the tail? Which side is the tail? Okay, let's say, okay, David again. His probability of getting, like a free throw, okay, on the free throw line, let's say it was like 40%. Okay, and we're gonna stand there and wait until he actually gets his first shot. Okay, and then we do this many different days until every single day we have a distribution. Okay, well the distribution look like this, normally distributed. Okay. Okay. So let's say, like first attempt, second attempt, third attempt, and then boom, fourth attempt. Okay. Or will it be, skewed to the tail on the right? So skewed right. Okay. Or will it be, you know what? He misses, and then many, many times it will be somewhere near the right like that. What do you guys think? Let's call this A. Let's call this B. Let's call it C. In seconds, talk to each other. What do you think the distribution looks like? Someone said D, yeah? Okay, okay. Okay. I decided to fail. Yeah. Yeah, number of trials you need until you get your first success. Okay. You ready for this? Okay. So again, the number of trials basically can be what? Infinite. Let's say this one day, we got in a car accident, became complete paraplegic. Okay. Okay, it can go up to infinity, right? Okay, so when you look at geometric distribution, you will always have a tail on the right side. Okay, everybody? Whereas on the left side, what's the lowest value you can have? Well, then you're not really doing anything. Okay, zero. Okay, zero. Okay, what's the next one? One. Okay, so would you ever have a left tail? No. Okay, so what that means is your distribution looks like this. Okay, every single, okay, the probability of getting it right is always highest in the first bar. Okay, for example, let's say David takes one shot, it takes him 40% to get it in. Okay, so far? Okay, what's the probability of him missing? So P is 40%, okay? So in order for him to get the next one, that means he needs to miss the first one, and then what happens? And he scores, okay? So for this one, it will be, now if he scores, it's 0.4. But if he misses, what do you need to multiply by? 0.6. Okay with that? So when you look at these two numbers, which one's bigger? 0.4, where the first time he gets it in, or the second time we had to miss and then score? What do you guys think? The first one's bigger, right? So okay with that? That means the next one, so this one over here is the second one. Okay with that? And then what's the third one? In order to score the third time, that means the first time you need to miss, second time you also need to, and then the third time what happens? You score. So this will be 0.6 squared and then multiplied by 0.4. Make sense, everybody? David, go ahead, yeah. Right now, we're treating everything as bars right now. Okay, you can't use normal approximation for this. Yeah, that's correct. Yeah. Okay. So therefore, hey, the very first bar is always going to be the highest. And after that, everything becomes what? Smaller, 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 smaller. This is the distribution of a geometric distribution. Okay? Two things you need right now. Expected number of outcomes is 1 over P. Okay? If you roll a dice, what's the probability of getting a 1? 1 over 6. That means that you go 1 divided by 1 over 6. That gives you what? 6. Okay? So you expected to roll 6 times and in order to get the first one. Okay? Make sense? Everybody okay with that? Right? You flip a coin. What's the probability of getting a heads? Half. So how many flips do you expect to have until you get your first head? 2. Okay? And then this one over here is your variance formula. Okay? And so for standard deviation, by the way, because it's not normally distributed, you can't use normal CDF. Okay? Now, but in case you want to know the variance, this is your variance formula. 1 minus P over P squared. Okay. Okay. Now, just write that down first. Yeah, yeah. P is probability. P is probability success. Yes. Okay. Yeah, that's correct. Everybody okay? Yes, no? All right. So far, if I remember correctly, there's only 2 main things I need to teach you about 8.2. And after that, we're done. Okay. In the meantime, who's missing? Sharice's not here? Okay. She's online? Okay, who else is missing? Mark Shabalov. Okay, yeah. Okay, anybody else? Gordon not here? Gordon skipping? Okay, Gordon. Okay. Okay. The reason I'm asking is if you're friends with them, can you fill them in? Okay, help them out. Anybody friends with Sharice? Actual real friend, like you're not actually, secretly hating her. Okay, one person. Okay, and then like, okay, Gordon. Anybody friends with Gordon? Huh? You're not friends? No. Okay. Okay, David, Mark. Do you take care of Mark?
Yeah, I'll take care of mine.
Okay. 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 Here we go. Okay. Geometric PDF. Now, geometric PDF means you're looking for the exact probability of you getting it correct. Okay. P is probability of success. X means what again? To get your first, this is how many trials you need. How come I don't need N? Yeah, N could be infinite. Okay with that? All right, so this will give you the probability of exactly, like, let's say what if X is? X is 3, you'll get your first success in 3, 3 trials, okay? CDF means what? Yeah, you take you 1, 2, 3, 4, all the way up to what X is. Okay with that? Sound good? Okay, so if my distribution looks like this, okay, here's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way through, right? If I want geometric, like say PDF, like X is 4, that means I'm only looking for the height of which bar? The fourth one, not this one, not this one, not this one, but only that bar. That would be PDF, okay? But if I want, CDF 4, that means I want bar number 4, bar number 3, 2, and 1 as well. Okay, so far? But what if I go 1 minus geometric CDF of like P over here, but 5? What does that mean? Everything after 5. So bar 6, 7, 8, 9, 10, all the way to infinity. Does not include 5, okay? Because 5 is included in this one, so it won't include it in the complements. Does that make sense, everybody? Okay. Okay, try this one here with your partner. Okay, everybody? Okay, these 2 questions. Okay. Suppose probably a rolling of 3 is 1, 6, and probably not 1, 2, 3, 5, 6. What's the probability of rolling your first 3 in your first row? Okay. A, B, C. 1 minute. Go. It's only 3 people? Mark, Therese, Gordon.
Missing a lot of people.
Huh?
They look really missing a lot of people.
Okay, just 3, yeah.
Why do I?
Okay.
Okay, we're done? Okay, first one. What's the probability of getting your first 3 in your first row? Okay, let's do this 2 ways. Number 1, if you were to give me an actual number, it will be what? 1/6. Okay, that's your answer, right? Now, if I were to use geometric, like would it be PDF or CDF? Okay, it is the same thing. Excellent. Okay, if I go PDF, this will be 1/6, comma what? 1. Okay, and now how come I can also use geometric CDF at the same time? Yeah, you start from 1, right? So either 1 in this case, they both work. Everybody good? Good job. Okay. Second one, what's probably getting a 3 in your second row? What would that be? Okay, as a number, what would it be? So 5/6 first, where you missed the first one, and then multiply by what? 1/6, which is your second one, is your success. Okay, buddy? Okay, would I use geometric PDF or CDF? So geometric, okay, PDF, this will be what? 1/6, comma what? Comma 2. Everybody okay with that? Yes or no? All right, okay, here we go. What's probably rolling your first 3 in your fourth row? This will be 5/6 to the power of what? The power of 3, and then multiply by 1/6. Who gets all this right now? Okay, and then, or you can go geometric what? PDF, and then what? 1/4. Any questions, anybody? Okay, 5 seconds. Ask the person next to you if any questions. Here, go ahead. CDF is when it's cumulative. Okay, let's say, oh, you'll get to it. We'll get to it. Okay, one more first. Yeah. Yes. You can just do this. Oh, okay. If I could be honest, some people can't do this. Yeah. Okay. In a way, this is much easier.
Yeah.
Yeah. If you understand, this is actually much, much more easier. Yes. Okay. It's just that sometimes we make questions that come in this kind of form. So be ready for that too. Okay. Because we can make questions where you have to like understand what that means. What? What? Okay. Okay. Here we go. Okay. Let's call this one A, B, C. Okay. Here we go. And do it both ways. Okay. Like for example, write it as a number, fraction, multiple, and so on, and also as a function using a calculator. Okay. Okay. You're okay with this? Yes, no? Oh, yeah, okay. Okay, first one, do you guys need some, hints or help or anything like that? No? Who's like, I get all three, Mr. Young? You just need more time. Okay, 30 seconds, go. Okay, I'll come around.
What?
Okay, can I talk about the first one? Okay, I'm coming around looking at answers, right? Okay, first one says, you roll a dice, what's probably take 3 or less rows to get your first 3, okay? So what I want you to do is, okay, now, I'll walk you through what most of you did first. I'll tell you what I think is the answer, and I'll show you what the best way to do this, okay? First one is, okay, who did this? 1/6 plus 5/6 times 1/6, and then plus 5/6 to the power what? 2, and then multiply by what? 1/6. Okay, who did that for your first answer? Okay, that's what most of you guys did. Okay, because it helps you understand, right? Okay, and then I'll show you what the answer usually looks like. Okay, geometric, with PDF or CDF? CDF, okay. And then it will be n is 1/6, and what is x? 3, okay? That's what some of you guys did, right? Now I'll show you what I think is the best way, okay? Ready? What you don't want is anything that requires 3 wrongs. Is that okay so far? Like, for example, these ones have 2 wrongs, this one has 1 wrong, and then this one has 0 wrongs, right? Now, can you do this on your calculator right now? 5/6 to the power 3. This will include anything that has 3 wrongs, right? And then go 1 minus that. And tell me if these values are the same or not. Go. Yes or no? Yes? Okay. So basically what I'm trying to show you is that this is what you want. Okay, so far? This part over here is your complement, because that will include every single outcome that has 3 wrongs, okay? Like 3 misses, okay? So if you scored in your 4th one, that you have like 3 misses. You scored in your 5th one, you also had 3 misses, okay? Just think of it as it's the formula that includes everything that involves 3 misses or more, okay? That's why 1 minus anything with 3 misses. Does that one make sense? 15 seconds, talk to each other. Can you make sure you write this one down? Okay, that one you need to copy down. Okay. Yes.
Does the calculator do it like calculating?
No, it just actually literally do the. You mean the algorithm it does, right? Yeah, I don't think it's that smart. It doesn't do that. Yeah, it actually runs through each one. So if you go like geometric CDF 1/6 like 999, yeah, it might actually crash. Yeah. Okay. Okay, next one. What's probably it'll take 5 or less roll to get your first 3, right? 5 or less. So therefore, this will be 1/6. Okay, you guys get the point, right? All the way to dot, 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 dot. What's the last one? 5/6 to the power of 4, and then multiply by 1/6, okay? And the other one is geometric, CDF. It'll be 1/6, comma 5, okay? And then, sorry, there's a 5, by the way, okay? And the other one will be 5/6 to the power of what? 5. So these are all the ones you don't like. It will have 5 wrongs, and then you go what? 1 minus that. Can you check in calculator and see if they actually give you the same values? Okay, buddy. All right. Okay, and last one is what's the probability it'll take at least 6 rows to get your first 3? Okay, so this will be what? Okay, so can I go geometric first? So geometric CDF. Okay with that? Geometric CDF. Okay, what goes 1/6, comma what? At least 6 rows, right? That means that you're gonna go 1 minus everything you don't want, right? So this will be a 5. Okay with that, everybody? Okay. So next question is, what if I want to write it in this kind of form, like these form? So what goes there? 5/6 to the power of 5. Okay, and that's it. Okay, so every single one of these outcomes have 5 misses. All right, so check again, see if it's okay, everybody. Okay, if you get this one, okay, we finished almost everything with geometric now. All right, everybody okay? All right. Can you maybe just check the person next to you, see if they understand this part? Okay, if you want to follow the math, like why does this work? It's basically a tree diagram. Okay, and then you do a geometric series. It makes it easier for you to walk through if you want. Okay, everyone good? Okay. Lydia, you're following? Okay. Talk to each other, guys. Okay. Yeah, it's too early. Okay. I'll bring coffee next time. Okay. I'll pay for it with my teacher salary. Okay. Don't be a teacher. You want a lot of money. Okay. Okay, let's move on. Yeah, I'm gonna skip this. Okay, I'm gonna blast through this. Okay. Can you look through this page and tell me if there's anything you don't get? Okay, go. Okay, 1 minute. Just quickly go through it. Any questions on anything on this page? Okay, geometric is X is geometric random variable. But there's 4 conditions. There's always 2 outcomes. Must be binary. B. Okay. The variable interest is the number of trials. That's N. Each observation is independent. So I. And the probability of success for each case is the same probability of success. Okay. And if you look at these, it spells B, I, BSNS. Okay, you can range it to BSNI or BSIN or IBSN or whatever you want. Okay. Okay, and it's not fixed. You can have infinite number of trials, and the histogram is always skewed to the right because the tail is on the right. You okay? Okay, you okay? Is everybody all right? Okay. Right. Anyways, okay. Can you copy this one now? Okay, not getting any success in the first like 5 attempts. This is the format I want you to copy now. Okay. All right. Pretty good. Okay, we're almost done. Okay. 8.2 finished almost. All right. Up to you. I thought you like you like having big tests or small tests? A big test. Okay. Small test. Okay. It's okay. Life will test you on this. Okay. Life in itself. All right. Everybody good? Okay, ready? 3, 2, 1. Okay. All right. Who's taking the AP exam? And you can see show of hands again. Okay. All right. Okay. Aiming for this. Okay. All right. Okay. So every year I make this I won't say deal, but more like a reward system, right? Okay. If the average of all the writers is 4.5 or higher, 4.5 or higher. Okay. Okay, 1 year we came so close, 4.41. Okay, 4.41. All right. That year they all looked at me and go, "What was the ice cream?" I said, "You didn't make it. 4.41, 4.5, still bit off." Okay. All right. I wanted to. I got them something else, like cheap ones. Okay. But if the average is 4.5 or higher, okay, you come back. I'm buying gelato. Okay. Not the cheap Costco stuff. Okay. Like gelato, like what's that one on Venable Street? What's that one? Like 1 million flavors one? The pink shop. Okay. One bucket of that, the last time I checked, was about $200. All right, $200, yeah. $20, okay? So I'm saving up for that right now, okay? Yeah, okay. I'm trying to say I believe in this class. Okay. Field trip down there? No, I'm gonna buy the bucket and then we scoop it, Yeah. Yes. Oh, you don't want ice cream. Oh, okay. That's too bad. You can watch everybody else eat, okay? All right, okay. All right. Okay. Now, when it comes to ice cream, okay, there's cheap like Costco, like little bars, and then you have gelato, quality, ice cream. Okay. If you go to Europe, set aside a budget, okay, of just gelato, budget, okay. So when I was there, $15 every day on gelato. Right? Okay, this one, 1, 2, 3, 4. We need to talk about. Okay, go. Okay, so for each one of these, you need to tell me, is it a geometric distribution? Yes or no? If it's yes, put down yes. If it's no, you need to tell me why. Okay, go. Insurance agent will keep phoning his clients, like potential clients. Just keep on calling until he gets the first person who will say yes to his plan. Like you call, hello, cold calling. Hi, my name is Shreya. Okay, I would like to introduce a new product our company supplying right now. Do you have any members in your family that would be interested in life insurance policy? Okay, for 20 years, you can be protected by X amount of dollars. No, okay, thank you. Bye bye. Next one. Hello, my name is Shreya. Blah 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 blah. Okay, okay, no, thank you. Bye bye. Hi, my name is Shreya. Get it?
Really? Are you sure? I don't. Okay. I don't think so. Yeah, I guess.
I think it's more
There's one.
it's not a concept of like everything you turn are abbreviation.
Well, the second and the third one I get.
Yeah.
And then the first and the last one.
First one, yes or no? Who says yes? It is, Mr. Young. It is geometry. Okay, I will keep on rolling a single die until I get the same number 3 times in a row. Who says yes? Okay, like roll it one time. Okay, a 2. Next one, a 2. Next one, 3. Oh crap! Start over again. Okay, who says no? It's not. Anybody here? One person around. What do you think?
Wasn't it like influenced? I mean, isn't it like influenced by the previous ones?
Thank you. So therefore, this one's what? This. Oh, sorry.
Oh.
This one is no. Okay, because not every. Oh, I forgot about Arnold, guys. Okay, yeah. Okay. Arnold, you okay? Okay, thank you for coming. Okay, you missed out. Okay. Okay, this one is no because first row, when you roll it the first time, what's probably a success of you actually getting 3 rows that are the same in a row? 0. Second time, if you're lucky enough to be the same as the first one, okay, but your probably success of ending in here is also 0. Okay with that? Next one, if the first 2 are not the same, what's your chance of success? Also 0. Okay, but let's say this is the same as the other one. The probability of success increases. That'll be 1/6. But if it's different from the other one, it's 0. Okay, so the probability of success for every single trial is not the same. BINS. It's not the same. So therefore, this one is no. Number 2, yes or no? Okay, let's say someone wants to find a prom date. Okay, he goes to a pool of people he wants to ask, finds the first person.
What's asked one person?
Yes. Okay, who says yes, it is?
Yes.
Okay, who says no, it's not? Okay, just think of it like this. Okay, this one is yes. Main reason why is because most people try to understand it as, well, let's see if I'm asking someone, like, would you come on with me? If he says no, okay, people are gonna be like, well, you said no, I'm gonna go to the next one. Okay, but the way we try to think of it as, okay, you say no, okay, put the name back in the hat. Anybody could be potentially asked again. So you go by the same person and go, can we still go now? No. Next second. How about now? No. Come back again. That could also happen. Make sense? Yes.
No, but like, what if like, let's say you ask them, right, and then their friend is like, "Yo, why didn't you go to Miss Young? You're like a big favor or something."
Okay.
Imagine what if that influences their like.
Okay, so the way we try to understand it is like this. Here's a population of everybody that you could ask. Okay, so far? If you pick someone in here, it doesn't matter what it is. They will always say what? Yes. Okay. These are the people that will look at Alex and go, you know what? I swear she would ask me. Because if he asked me, I would definitely say yes. Doesn't matter what anybody says, okay? Just because he's so okay. But everything else he'll be like, Alex, ew. Okay, why would I go with him? Like, okay. Okay. No, definitely not. Okay. So when you pick someone, okay, you can pick someone here. That person says yes or no. It will not affect anybody else coming inside or outside the circle. That makes sense? Okay. Sound good? Okay. Yes or no? Okay, here we go. Number 3. Sorry. Okay. This is no. This is yes. Number 3. Insurance agent will keep forming his clients. Now, when I say clients, I'm talking about potential clients, like cold calling. Okay. Until she finds her first client. Okay. You guys get this? This won't be what?
Yeah.
Is it binary? Yes. Is it each one independent? Yes. Is it, an infinite number of outcomes? Yes. It could be like nobody, like, and it's the probability success the same. So this is yes. Okay. Number 4. Okay. What's the main issue with this one? Yeah. Every day you drive it, the probability success increases, right? So therefore, which one doesn't work? Is it B, I, N, or S? S. Okay. This one is not same probability success. This one is no. Okay, everyone? Okay, 15 seconds. Ask the guy next to you, girl next to you, if they understand all these 4. Okay, go. Because when you drive the car one day, yeah, even that slight change the probability of success is different every single time. It's not independent. Okay. Yeah. So how you drive today could affect it tomorrow, or every time you drive it, you're more likely to break down.
100 people, and everyone said no.
No.
That might change the
So the difference is no. The difference is everybody inside is yes, everybody else outside is no. The trials are you randomly pick someone within the box, okay, and then no one will come in and out. Same car though, same car. Yeah, you drive the car for 100 kilometers, and then the chances of breaking down increases the next time. Okay. Yes, David. Yeah.
Doesn't 3 times in a row technically count as 3 successes or?
No. Like you have to keep rolling a single dice. Yeah, you're not rolling 3 dice. Rolling a single. That's the key thing is this: you're rolling a single die until you get roll. If I talk about you're rolling 3 dice at a time, then the answer will be yes. Okay. It's a very different scenario. Yeah. That one's easy. This one not so much. Okay. All right. Here we. This one explain. Okay. How about? Gosh, what else is there? Is it this one here? This is the same question. You want to try this one too? One more time? Okay. Large companies hiring and will continue to interview candidates until someone suitable is interviewed. Okay. Suppose the probability that any candidate is suitable is 1/9. And then every candidate is independent of one another. Find the probability for the following: A, B, C, and D. Okay. This is just to ensure that everybody gets this. Okay. Go.
No, that's wrong. So like, you know, one file is going through.
That was your one single dice break. Like if you rotate 3 dice out and then they did it.
That could be, but then you only have one dice.
Because of each roll.
Yeah.
Like if you roll 3 of them at once, it's like one.
If you package like that, saying every 3 euros, it's a single dollar and it might be actually pretty professional.
Even that you was not that suitable candidate, right? If you were following
So what my first
Oh, first, first 10 minus.
I got one. You already told.
The only one is like doing like this.
It's like this, do like this, and then we also 5 over 6, no.
Yeah.
8 over 9 to the power of,
Give that suitable candidate.
8 over 9 to the power of 12 and over again.
So what you won't find the first word, you will find the first.
Hello?
So you just can't find it. You really can't much steer.
So fourth one is point one.
Yeah, I thought that's.
I don't need it for this.
Okay, so geometric shell is
Yes.
so geometric like so everything capitalized, yeah, 100 times all the times
The third one is one for you on.
Wait, 31, wait,
First, that would be great.
how do you do that?
Just the first head minus the first one. Probably
No,
the
so
first head minus.
1 minus the first. It should be.
If you're doing one minus the first one, it's after one, not the You need to know 10 and -4, so that.
Oh, -4, so it's just,
Make 5 to 10.
out. Good? Oh, what's that? I actually kind of went off.
Geometric PDF is the, what's next?
Let me see.
What?
No, no, like, actually.
Oh, what's?
So.
So you just take yeah, that it is within the first 10 and then -2. You can take the last one. Hello, what? The last one?
Yeah.
The last one.
Like PDF also is exactly 5 over PDF over 10.
Within the first 10, but not with foot.
You're given that it's about the first 10.
Yes, but there's a much faster way too also, okay? Yeah. Okay, you guys ready for this one? Okay, first one. What's the probability that a suitable candidate will be found within the first 8 interviews? That one's obvious, right? Geometric, PDF or CDF? CDF, it'll be 1/9, right? Comma what? 8, okay. Now, if you write it in fractional form, it will be 1. Sorry, no, is that 1? Okay, or 1 minus what? 1/8/9 to the power of 8 is correct. Okay, good job. All right. Second one. What is the probability that a suitable candidate will not be found in the first 12 interviews? So this one also 1 minus geometric CDF 1/9, comma, what goes here? Will not be found in the first 12 interviews. It will be 12. Okay. Yeah. So in the first 12 and 1 minus that. All right. And what about this one here? This will be 8/9 to the power of 12. The 12? Yeah. Pretty good. Okay. Now C, a little harder now. Ready? Okay. When you look at C, which word makes C difficult? Given. Because it's given, what kind of question are we looking at? A conditional probability. Okay, so far, given that you will not find a suitable candidate in the first 4 interviews, that means the first 4 are automatically given to be failures. So you can ignore that, okay? So I'm gonna draw this out. So that means that, okay, here's the first bar, second bar, third bar, fourth bar, fifth, 6, 7, 8, 9, 10, 11, 12, and so on, so on, right? But you're told that, hey, the first 4 are basically what? No, right? So that means that 1, 2, 3, 4, these 4 bars, what's the probability of success for either one of them? 0. These 4 are gone. Okay, so far? And then it goes, what's the probability you find a suitable candidate within the first 10 interviews? That means that you want, okay, so that means the only ones that are possible is like 5, 6, 7, 8, 9, 10. And then you want like this, all this divided by, okay, let's call this A. A is everything from 10 and over. Divided by what? Divided by this part over here where everything is 5 or more. Okay? Yes or no, everybody? So given that. Oh, sorry, my bad. My bad. Think of shit. My bad. Within the first 10, so it's not supposed to be A. What should it be instead? So I only want this part over here, which is going to be what? It'll be 1 minus A. Yes or no so far? Okay. Divided by all this over here, which is B. Yes or no? Okay, buddy? Did I lose anybody? I lost some people? Okay. All right. Okay. You know what? I'm going to. Okay, hold on. I'm going to highlight this one. This is the second thing I need to show you. Ready? Okay, here we go. Ready? Okay, here we go. AP stats. AP stats. All right, here we go. Okay. You work for a company. You want to look for people to hire. You want people who are good, not people who suck. Okay. So first person here, what's probably success in the first trial? It's supposed to be this high. Okay. What's the height of this bar? 1/9. 1/9. Second bar. Okay. Now nothing's given yet, right? This will be 1/9 multiplied by 8/9. Second bar. Okay with that? Third bar, fourth bar, fifth bar, sixth bar, seventh bar, eighth bar. 1, 2, 3, 4, 5, 6, 7, 8. I'll draw a 9. I'll draw a 10. I'll draw 11. I'll draw a 12. Draw a 13. Okay with that? Okay, first question goes, given that you would not find anybody in the first interviews. That means that first bar, second bar, third bar, fourth bar, what happened to all of them? Gone, done. Like nobody good was there. Okay, this part's gone. Okay with that? Now the question goes, hey, what's the probability that you'll find a suitable candidate within the first 10 interviews? That means I'm looking for this one, this one, this one, this one, this one, and that one. That's what you're looking for. Okay. So two ways to do this is find the probability of all this and then minus what? Yeah, minus the first four. Is that okay? Okay. Tell me what that gives you when you do that. Okay, so geometric CDF, right? It will be 1/9, comma what? 10 minus geometric CDF, and then 1/9, comma what? 4. Okay, and what does that give you? Okay. I think this should work. Given that I'm thinking right now. It's one of these. Okay, yeah, divided by. Okay, because it could be anything from here, right? Yeah, 1 minus geometric CDF, and then what goes there? 1/9, comma 4. Can you guys do this right now? Tell me what it gives you. Okay. So you're looking at the probability that it's over here. The probability is over here. Okay. Given that it's over here. Okay. From here all the way to there. Okay.
So we find within the first 10.
No. Yeah. Okay. The top part is just the probability of getting success between 5 to 10. Okay. Probably find to 10. Okay. But the thing was, this question here is not just finding it from 5 to 10. You're given something. You're given that that it cannot be any of these ones. Okay. So therefore, this part is the given part. Okay. Because whenever there's conditional probability, the denominator is what is given. Okay. Yes, David. Go ahead.
Does anyone have the decimal value?
What does it give you?
Okay, wait, so what I did is just geometric CDF of 1/9, comma 6.
Yeah. 1/9 geometric.
Yeah, just one
Geometric CDF.
CDF, 1/9, comma 6. That works. You just ignore the first 4 and you start later. That's the same.
I will come over and discuss with you. Okay, promise you. I'll come over and discuss with you. Okay. All right. Okay, how about this one, David? This one, D. But this one, okay. Given that a suitable candidate was found in the first 10 interviews, okay, the first 10, what's the probability it was found in the 5th interview? No, because the prob success for each successive one is going to be smaller. Okay. Yeah, it's not. It's the prob success for each number of trials is not the same. Yeah, you can only use that formula when every single outcome has an equal chance of success.
I provide my geometric CDF for my hand.
See there? That's how you.
Okay, D okay? No? Okay, so what's given? Given that one of the candidates was found in the, okay, so that means the denominator is going to be geometric, CDF, it'll be 1/9, comma, 10. Okay, so that means it must be one of those, right? But I'm looking for a geometric, what, PDF or CDF? PDF, and what's on top? 1/9, comma, 5. Okay, buddy? All right, the conditional ones are okay. David, I'll get back to you on that one, okay? All right. Okay, let me see what else is there. Everybody good? Okay, other than that, everything's all here. Uh, okay. Mean and standard deviation. Okay. Okay, other than that, okay, I don't know if you're interested in finding the proof for the mean. It's all over here. You can read it yourself. It's all typed for you. And then this one I think we can skip. Okay, can you make sure you watch the rest of these? Okay, and I'm gonna skip this part, okay? All right, can we move on to chapter 9? You guys ready? Okay, 9.1. What time is it? Okay, 1 hour in. Okay, 1 hour. Ready? Okay, 1 hour in. Okay. All right. 4 o'clock, 10 to 12, right? Okay. Yeah. Okay. Ready? Here we go. Okay. Shh. Now, okay. We're only missing 3 people, right? Okay, again, if one of those 3 that are missing is a friend of yours, you need to fill it in 9.1. You ready? Okay, here we go. Right now, can you copy down this word? Distribution of sample means. Distribution sample means, okay? Okay, and I'll give you a heads up what's going on, okay? All right, ready? Distribution sample means, okay? Now, a distribution of something, a distribution of all possible sample means, okay? Now, okay, two things, okay? Let's say if I want to look at the average weight of like grade 11 and 12 students, okay? Average weight of grade 11, 12 students, okay? The variation could be quite big, okay? Some people are like quite unheavy, and some people are quite heavy. Okay. All right, okay. Anyways, the distribution could be something like this. Okay. Let's say there's no 0 there, okay? This is distribution, okay? And you can argue that, hey, maybe the average weight of everybody is 130 pounds. 130 pounds. Okay, this is the average weight of all high school students. Everybody okay? Yes or no? Okay. And then if I were to look at standard deviation, hey, this will be 115, and this will be 145. This is one standard deviation. Okay, like most students will range from here to here. This is when the sample size of each person you're looking at of 1 n is equal to 1 means that you look at each individual, one person. Yes or no? Okay. Now, on the other hand, no. So this is your population, okay? And this is the population mean, okay? Now, second part now, you ready? Okay, shh. Come on, no zoning out, okay? This part you need to focus, okay? If you can't focus, just help yourself, okay? Okay? Until it works, okay? Ready, here we go. Let's see, on the other hand, if I don't just take one person, I take a class of 30. So what I do is this, okay? I would take 30 students in the class, everybody, all the really heavy ones and all the unheavy ones, put them all together, average them all out, okay? Average them out, okay? So what you're doing is you're not looking at individuals. You're looking for averages of 30 people, okay? So you take an average 30, okay? Now, if you look at the distribution of these averages, that's what a distribution of sample means. That's what it means, okay? Is you have a bunch of averages and you look at the distribution of possible averages, all right? So look at number 1, okay, question for you. When you look at the distribution of averages, I'll give you 2 options. Number 1, will it be, here's 130 pounds. Will the mean be smaller than 130? Will it be bigger than 130? Or will the mean be around 130? A, B, C. Talk to each other, go. No, you're not looking at one specific. You're looking for all possible averages 30s. Okay? What's that?
130 above the average.
No, I'm asking you, is the expected average going to be at 130, smaller than 130, or bigger than 130? Okay, you ready for this? The answer is, okay, when you look at the distribution of sample means, it will always be the same as the population mean. It will not be different, okay? There are proofs for this. I'll walk you through that later on, okay? So number one, the answer will be, it will be C, okay? The population mean and the distribution of sample means must always be the same. That's number one, okay? And number two, okay? So basically look at all different averages you can have, right? And then you plot it out, okay? Number two, will the distribution, okay, the variation be bigger, like more variation, or less variation, or it'll be the same amount of variation as the population? What do you think it'll be? Okay, will it be 1 bigger, 2 the same, or 3 less variation? Go. 15 seconds.
Oh,
I think it's hot, but I don't know what it was. Now it's-
What percent was that?
I would be in the far right. Far right, yeah. Yeah, very far to the right. I know. Yeah.
Like also part.
Yeah. Yeah. We know what's up. Food loves us, we love food, yeah. Yeah. Genetics, can't help it, yeah. Habitual lifestyle, yeah. Yeah.
Oh, I have.
So what do you guys think? Will there be more variation, less variation, or the same? Who says more variation? Who says it's the same? Who says there's less variation? Ready for this? The answer is whenever you look at averages, there will always be less variation. Okay with that? Now, the key thing is this, okay? So I have two ways to explain to you why is less variation. Okay, you ready for this? Everybody good? Okay, here we go. Okay, I'm gonna erase all this right now, okay? Now, 10 seconds. You just watch this right now? Okay. Let's say right now, okay, the average is 130. Okay, average 130, right? Now, let's say the 5 heaviest people, okay, 5 heaviest people, okay, the average, okay, the weights are gonna be 180, 185, 190, 195, and 200 pounds. Okay, these are the 5 heaviest people, right? Okay, so that means that the maximum is 200, right? But if I were to take the average of these 5, what's the average of the 5 going to be? It will be 190, the middle one, right? So what happens is when you take the average, then the maximum, will it get bigger or smaller? The biggest value gets smaller, yes or no? So just push this way. Okay, let's say you look at the 5 lowest people, okay? Okay, I'm making this up, this is not real, okay? Let's say the 5 lightest people are gonna be 5 pounds, 10 pounds, 15, 20, and 25. Let's say these are the 5 lowest people, okay? What's the minimum weight right now? This person hasn't eaten since they were born, okay? Okay, there's nothing, okay? Okay. Anyways, you get the average of these 5, so what would the weight be? 15. So what happened to the minimum? Did it go up or down? It went up. So therefore, the variation, did it increase or decreased? It decreased. So number one is when you're looking at the distribution of averages, it always decreases the variation. Make sense? Number one now, okay? Number two, oh, pen just died. Number two is this. Okay. Number two is, oh, pen just, oh, I need a new pen. Anybody want to sponsor me? Oh. Well, if there's no pen, then there we go. Pen. Okay. Okay, here we go. Now, second thing is this. Okay, ready for this? Okay, number one, this is for population. If you're looking at individuals, what's your sample size always going to be? So for individuals, sample size will be 1. That means that you're just measuring one person at a time. Okay, that's what it means to look at the population. Okay, so in the population, this is your mean, and this is your standard deviation for the population. Okay, second one is this. When you look at the distribution of sample means, now this is a new term. This is the mean of a distribution of a bunch of averages. Okay, the distribution will be having the same mean. Okay, but the standard deviation will be smaller. What I need you to copy down is this. The standard deviation for the distribution of sample means, meaning like the standard deviation of this second one will be equal to your population distribution divided by square root of n. Who's seen this one already before? Okay, so what that means is when your sample size get bigger, the variation becomes what? Smaller. Can you write it down somewhere? Okay, when the sample size, not population, when the sample size get bigger, okay, the range of averages become smaller. Sure, go ahead.
The number of
Nope, n is a sample size
why is the n equal to 1 for the population?
because you're only looking at a sample of 1 every single time. Okay. All right, so one individual. Oh, the weight is 185. One person, okay? Next one. Oh, Amber, okay, the weight is 120. Okay. Next one is, let's say, I don't know, Bowen Zhang. Okay, the weight is 250. Okay. Next one is Cody. Okay, someone over here. Okay. Next one's Alex. X over here. That's individual, right? The second one is I take 30 people. You 30 over here. The average is actually about 131.2. I go to the next class. The average is actually 133. I go to Chang's grade 8 class. The class is about like over here. Next one's over here. So every single dot is an average of 30 people. Okay with this? Okay, this part over here, if you get, good. If not, when you guys talk to each other, ask them to understand what's happening. And I'll walk. Yes. It's distribution of averages. Okay? Everybody okay? Okay, you don't, okay. Okay, I'll be funny. Okay, this concept is what almost everything in this whole course is based on. Okay, it is a distribution of averages. Okay. Okay, everybody okay with this? All right, is he good? All right, here we go. Okay, number 1, what's important? This lesson is the introduction to inference. Inference is basically you're using your one sample, okay, to make estimates about the population. Okay, everybody? This part over here, you need to copy down word for word. Okay, what do you think the keywords in this sentence is? Okay, inference is one of them. What's the second one? Estimation. Okay, you're always using your sample to estimate your population. That's why when you have a sample, everything is called an estimator. Okay, you're estimating your population. Okay. Okay. Suppose you don't know population mean. You take samples to estimate the population mean. But the thing is this, how many samples do you take? Okay, now in general, remember this, practically, you only take one sample. But theoretically, you're thinking of as if you took an infinite number of samples. Okay, you guys ready? Okay, so this one here, big, okay, 1 hour, okay? Ready? Okay, introduction to the concept of distribution of sample means, or sampling distribution. These two terms I've underlined, they mean the same thing, okay? Sampling distribution or distribution sample means that imagine you have an infinite number of, not infinite, you have like many different samples of the same size. And you look at the distribution of their averages, okay? That's what distribution sample mean, or sample distribution, can't say this. Just bear with me, okay? They mean the same thing, okay? When we take a bunch of samples of fixed sample size n and use sample means to create a density curve. That's what's going on, okay? This density curve is a distribution of all possible averages from the same sample size n. And then no one repeated this, but can you make sure you underline this over here? all the samples theoretically should have the same sample size, okay? It cannot be, these ones are size 30, these ones are size 50, and then we create a distribution. Doesn't work like that, okay? And essentially, and then this part, okay, you will be guaranteed to have a test question on this, okay? So the central limit theorem indicates that the distribution of the sample mean is normally distributed, okay? But the key thing is this, certain conditions must apply, okay? If these conditions are not met, that means the distribution of your sample mean will not be normally distributed, okay? The key question is this, why does it need to be normally distributed? Yeah,
Because it's already an average. So you're getting.
why is it important to be normally distributed? Yeah, no, okay, good answer though, but no. So remember this, if something is not normally distributed, you can't calculate any of the probabilities using normal CDF. So it doesn't work. So it's pointless. Okay? Does that make sense? So you want it to be normally distributed. But the thing is, if it's not normally distributed, then you can't make these calculations. Yes or no, everybody? Okay? Okay, so the key part is this. Okay, now in this whole entire sentence, I've underlined in the bottom, and then the bottom over here. What do you think the keywords are? Okay, actually, no, not that one. Not normally distributed. What's the keyword? Okay, its first part is this. You see this over here, central limit theorem. You need to write that down somewhere. Okay, and I'll walk you through word for word what the central limit theorem actually says. In general, what it's telling you is that the distribution of your sample means would be normally distributed if what? If what? Okay, some of you are gone already. Okay, what must happen? What does it say? Certain conditions. Can you underline this word? The key word is the word conditions. What are these conditions? And then when terms conditions, from now on, whenever you answer a question, you need to tell me whether if these conditions are met or not. Okay? And with AP, it's important that you answer like which conditions are met and not met in full sentences. You lose marks if you honestly, if you have asked your conditions, you lose marks. It's what separates a 4 from a, or a 3 from a 4. Okay, you get this? Okay, so your understanding if the conditions are met or not will separate whether you actually understand what's happening. Okay, yes or no, everybody? Okay, the next couple slides I'll walk you through what these conditions are. So basically, what I'm trying to tell you is you need to fully grasp what the conditions are. Yes or no? Okay, everybody talk to each other 5 seconds. They understand what I just said. Can you help him like he just knows? Okay, ready? Okay, 2 more terms you need to know, okay? First word is parameter. Parameters are, okay, whenever you use the word parameters, it just describes things about the population. Okay? Anything you want to know, okay? Like population mean is a parameter. Population size, parameter. Population standard deviation, also parameter. Okay? Things you know about your population. Those are parameters, okay? The word statistics. A statistics is anything to describe a sample. Sample mean is a statistics. Sample standard deviation, statistics. Okay? Sample size, statistics. Okay? So the whole goal is you're always using your statistics to estimate what? Parameters. Okay? You know about the parameters, you're making big bucks. You know about statistics, you basically know nothing. Okay? All right. The whole goal is you want to collect enough statistics so that you can know about your parameters, and then you can make your. Okay. So a student of mine in New York right now works for Hudson River, and basically when we're talking, sometimes he says that all he does is every day he has these big giant supercomputers, and he's just combing data, like combing data. Okay. And all you're doing is you're combing a bunch of, you're just combing a bunch of Oops, I lost. Combing a bunch of statistics. Okay, these were his words. A bunch of statistics. Okay, and the whole goal is you create a model and use the models to represent the parameter. If your model is good and it's accurately representing your parameter, that means that you're going to be making. Okay, okay, life is good. Okay, but if your model sucks and you don't have enough statistics to estimate your parameter, then you make a big mistake, and then okay, make sense, everybody? Okay, all right, here we go. Oh, so. My bad. Okay. I just want to show you how many sides there are. There are just a few.
Just a few, yeah.
Just a few.
We have
Just a few.
14 minutes.
Just a few. Okay, up to 9.1 then. How's that? Okay. I'm losing some of you guys. You want to come back another day? No. Okay, fine. Okay, don't bother. Yes, yeah. Yeah, 12 by 12. Yeah. Okay. My time is almost up. Okay. Yeah. All right. Ready? Here we go. Okay. What is a distribution of sample means? Okay. So this one over here, I want you to watch this. Let's say my population is people in North America. Okay. So anything about parameters, it's about the population. Okay. So suppose you want to find the average height of all males between 24 to 35 in North America, right? So to get this population mean, you will need to do several things you can do. Number one is you take what? You have a jacket? Okay. Okay. All right. Put it on. Okay. Here we go. A census basically is what you ask what? Everybody. You survey every single person. Okay, so far? And then this is your population mean. Okay, so far? Now, what if you took samples of size 30 and map out the distribution of the averages? Okay. Now this one just watches. Okay. It's like this. Here's one sample of people. You have an average of 170, and then boom, there's the average. That one with that one group. Okay. You stick all these people back inside, okay? And then you do another one, okay? Another group of 30 people, right? And then you have an average of 174. And then boom, you have another one, okay? And then you take another average, and then so on. No, this is theoretical. It's what you would understand how things are supposed to look like. But that's not what you do, okay? Because in practically, how many averages do you actually take? No, you just take only one sample, okay? But theoretically, you take like let's say there's 10 million people. So it'd be 10 million, choose 10 million, choose 30. And that will be that many separate samples. Okay. Anyhow, and you keep on doing this. There's the next sample mean, and then you keep on going. Another sample mean. Okay, and then take that one, and then that one, and then that one, and then that one, and that one, and that one. Okay. So basically what's happening is these are all the possible averages. And then what you end up getting is, what do you call this over here? A distribution of sample mean. That's the first way of saying it. What's the second way? A sampling distribution. And what you end up getting is, so what you have now here is called a distribution of sample means. Okay, so far? Just remember that this will be useful. Okay? Just keep in mind that population could be normal. The distribution of sample means will be normal. Okay? The population is abnormal. Okay, whatever. Okay, final, bimodal, whatever. Okay, if the sample size is big enough, the distribution sample means will also be normal. Okay? Okay, population trimodal, uniform, skewed, okay, abnormal, whatever. Okay, as long as your sample size is big enough, 30 or more, the distribution sample means will be normal. Make sense? Okay? Yes or no? Okay. So the mean of the distribution sample means is equal to population mean. So what I need to copy down is this. This part, you need to copy down. Okay? And for those who are interested, like you actually like math, okay? Tell you what, go home, see and prove it, okay? All right? Yeah. The PowerPoint actually walks through, like, I'm going to skip that part, okay? Why is the population mean equal to the distribution of sample means? Okay? Okay. Cody's like, I'm thinking already. Who's actually interested in learning how to like, who wants to try this on their own? Yeah. Okay. One and a half. One and a half. Two and a half. 3.5. Yeah. Okay. Go home. We'll discuss it later on. Okay. All right. If you want. All right. Move on. Okay. What's important? Number one, sampling distribution. Okay, this concept is important. Write it down, okay? So the distribution of all possible sample means of size n from the same population. First concept. That's what sampling distribution is. Number two, the mean of each sample you take is known as this. The X with the bar above is a sample mean, okay? Every time you take a different sample, the sample mean will be what? The same or different? Different. You have a different classroom, the averages becomes different. It could be more or less. Sample means don't stay the same. They're different for every different sample, okay? Okay. But in terms of population mean, you only have what? One of them. It's where you include everybody and you get the average. Only one population mean, but many different sample means. Okay. This over here that I circled, is it a statistics or a parameter? Statistics. This over here that I just circled is going to be what again? A parameter. Make sense, everybody? Okay. So the goal is you have of these X bars, you have enough of those X bars to estimate population mean mu. Okay. By the way, if you change your sample size, like a bigger sample size or a smaller sample size, the sampling distribution will also be different. Okay. Now, these are all concepts I need you to copy down. Okay. They're all useful. They're all like, you're going to get questions where you're going to be using any one of these. Okay. All right. Standard error. Okay. Standard error now. Okay. Now, this is a term to describe the standard deviation of your sampling distribution. Can you write this down? Standard error. And you will see this a lot. What is standard error? Standard error is the standard deviation of your, like, when you look at sampling distribution, it's normally distributed, right? That's the standard deviation of your sampling distribution, okay? Standard error is the standard deviation of the sampling distribution. And the key thing is this, it is always smaller than the standard deviation of the population. And the key idea is when you're looking at averages, you always have more or less variation. Always less variation. Okay. Everybody good? How much more time do you still have? I have half an hour. Okay. 30 slides to go.
Okay.
Okay.
Wait for a minute.
30 slides to go. Anybody here planning to study, like, major in stats at all? No? Yeah, okay. Oh no, yeah. Okay, one. All right. Okay, when you do study it, come back and let me know how it goes. Okay? Yeah. Yeah, I want to know, like, when you go to job fairs, let me know how it goes too, okay? Where you plan to go?
Fans, an actuary in New York.
New Yorker. Oh. Okay, is she gonna pay for education too?
Huh?
She gonna pay for, she can teach you? Okay. Okay. What do you plan to study? Yeah? SFU has a good program there too. You applied?
Yeah, they have accepted.
Okay, okay.
They haven't accepted.
All right. What'd you apply to? Oh, okay. So they're like a geometric distribution.
Yeah.
Okay. All right, okay. All right. Okay. Keep applying until you get your first one. All right. Okay. I just know that in the last couple of years, because of political reasons, it's been harder for local students to get into university. Yeah. And the main reason why is because a lot of students technically would have gone to the States, and because there's a certain population of them that decided to stay here, so they increased the bar locally. Yeah. I was hoping that two things happening. Number one is because of what's happening in the States. Second one is 2 years ago, they reduced the number of students allowed into Canada. And at first I thought that's going to increase the acceptance rates in Canada. But unfortunately, that's not what's happening. By reducing the number of international students, the amount of money going to like secondary institutions, it didn't go up, instead it went down. So funding, like the amount of resources they have in post-secondary has also gone down. So there've also been a lot of layoffs. And as a result, the number of spaces has also gone down. And that's also hurt local students as well. Okay. Well, my suggestion for you is Anyhow, okay. SFU is pretty good. Okay. Yeah, I have some students that graduate from SFU from the actuary program, and they're actually doing quite well. Okay. Anyways, and in case you don't know what actuaries are, okay, I get that most people only apply to jobs or apply to things that like the people around them know about. Like for example, your parents don't know what actuaries are, they're not going to encourage you to go do something like that, right? So what happens then is these high paying, like high revenue, like positions, they only get exposed to a certain population of people, right? So actuaries, what they do is they manage risk, basically. Okay. Yeah, how to manage risk so that, and then also look help a company. Let's say you go to business. How do you prepare your business like for years ahead so that in case anything happens, your company will still be able to survive? Okay. Economic downturn, be able to survive. Okay. How do you plan for these things? Okay. It's one of the high paying jobs that I know about. Okay. Yeah. If you're interested, you need, okay, Central Limited. Yes.
BTIT is it good?
Okay. Anyways, everybody okay with this? Okay, here we go. Okay, so again, if you haven't copied this down, is the mean of the sampling distribution. In case you don't know what this is a mean of the sampling distribution will be equal to the mean of the population mean. This is a key point. Why is this useful? If these two are not the same, okay, then everything else is useless. Okay. So when I try to predict like for the next coming years what the stocks market is going to look like, I try to look at the projections of individual stocks and I randomly select 30 of them. And then I get that average, okay? And I try to use that to predict, okay, this coming year, what do I expect to see? Like a practical value, okay? So knowing what the general market, which way is going to turn, up or down, whatever percentage, will influence what kind of price I set for each stock moving forward, okay? So this is something we'll talk more about. Using a confidence interval of your of what you think the projection of the market is going to look like can be used to help you assess the value of a stock. Okay. Sound good? Okay. Yeah, I'm not BSing this part. Okay. Yeah. Okay, here we go. Okay, number 2. Okay. This one here. Okay. Shh. The distribution of your sample means should look normal distribution again if certain conditions are met. I should jump straight to conditions, okay? But in the meantime, okay, here we go. Okay, here are the ones. Number 1, it must be a simple random sample. If it's not a simple random sample, that means the way you're selecting your sample is biased, okay? So how you select your sample is very important. It must be a simple random sample. Every single individual is equally likely selected, okay? Number 2, your sample size should be at least 30. This is only needed if your population is abnormal. Uniform, trimodal, bimodal, skewed, then you need your sample size to be 30 or more. But if the population is normally distributed, okay, if the population is normally distributed, then you don't need the second part, okay? Your sample size don't have to be 30. There's an app I'll show you like when we have time, okay? And why is this true? I'll literally show you that, hey, if it's 25, it will be somewhat approximately normal, but not as nice as if it was 30 or more, okay? This one here, okay. This one is the one where most students have a hard time with. You know what capital N stands for? Capital N is the population size. What does little n stand for? No, not number of samples. Little n is the size of your samples, okay? Like 30 people. or 25 people or 50 people, okay? Not the number of samples, okay? And remember this, your sample sizes cannot be too big. If your sample size is too big, that means that there will be no variation, okay? So your sample size must be less than 1/10 of your population, okay? This one over here, important, okay? And that one's used. If this is not true, you can't get standard error. You won't be able to get a standard deviation formula, okay? So we'll talk about that later on, okay? Okay, and in case you're wondering what is standard error, this is standard error. The distribution, the standard deviation of your sample distribution. This is equal to this over root n. That is standard error. If this is not true, you can't use that formula for standard deviation. Make sense? Pretty okay? Okay, anyways, so here we go. Okay. Okay. So anyways, I'll let you copy this first before I move on, okay? So again, this over here is standard error. Standard error, just another way of saying standard deviation, but not for the population, but for your what? Sampling distribution. Okay. Beautiful face. Beautiful face. So nice. I've had students who are already like established in certain fields. Would you guys want to talk to them? Like you want Hong Kong law, right? I can just email, get him his email right away. Yeah. Yeah, he's in his third year right now. You can talk to him. Yeah. Okay, you already have people. Okay. I'm meeting with him. Okay, okay. I have a actuary visiting next month. He's actually very established. Yeah, come by like in February. We're gonna have lunch together. Yeah, you want his. And if you care to, you know, you can ask him like 100 questions. Yeah, smart guy. Smart guy. Okay. Anybody else want to go into stats or anything? Nobody? No? Your family are really smart. Okay. Yeah. How's she doing right now? Still unemployed? Still employed. Doing what now? Oh, okay, okay, okay. She happy with it? You think so? Okay. All right, good. Okay. Happy with the money. Money should be good. Yeah. Yeah, she's pretty smart. Yeah. Okay. Yeah. I'm talking about your sister. Yeah. Yeah. Okay. Yeah. You're pretty good too. Yeah. Okay. 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 All right. Anybody else okay? All right, here we go. Other things you need to know. Okay, next one is this. Okay. First one is when you look at sampling distribution, here's the key point, okay? This is the population, okay, so far? If my sample size is 30, okay, then what happens is your sampling distribution will look like this, okay? There's the sample distribution. The variation, again, is what? Smaller, okay? And again, if I take the same population and if I were have to have sample sizes 50, then what happens then? The variation gets bigger or even smaller? Even smaller, yes or no? Okay, so the key formula is this. With a bigger sample size, your sampling means will be closer to the population mean. So that means that standard error definitely becomes smaller, okay? So you need to copy down this formula. This is the formula for standard error if you don't have that already, okay? Okay, and can you check each other's notes? Do they understand that standard error refers to the standard deviation of your sampling distribution, okay? These terms, you need to get them right. It gets messy, okay? That's where things get ugly from now on, okay? How do you find your confidence interval? You need standard error, okay? How do you do hypothesis testing? You need standard error, okay? Okay. Everybody good? Okay, move on. Okay, so why is 50, like the center for 50, smaller than 30? And the reason why is because n is in your denominator. When the denominator gets bigger, the value becomes smaller. Okay? So dividing by root 50 will give you a smaller value than divide by square root of 30. Okay? Yes, no? Understand? Yes, no, anybody? Okay, move on. Here we go. Okay, this slide not as important. Okay, here we go. Things that you need to copy down. Parameters. Everything that has to do with the. Okay. population mean, population standard deviation, population variance, population size, and P is population proportion. Okay, these are all the things you need to copy down. Proportion is where what percentage of the population actually are diabetic. Okay, like 30% in North America. Okay, or what percent of the population are actually high blood pressure or hypertension. Okay, 60%. Everyone's dying. Okay. Anyways, the next one, statistics. Sample mean, sample standard deviation. These are all notations you should copy down. Okay. S is sample standard deviation. Variation is S squared. Sample size is little n, and sample proportion almost the same, but it has a P with a hat. A P hat is your sample proportion. Okay. Third one is sampling distribution. Just keep in mind that this is the mean of your sampling distribution, and this is the standard deviation of sampling distribution, also known as standard error. Okay? Make sure you write down these terms. Don't get confused. Okay? And again, the goal is to use this to estimate what? This. Okay? Now, here's the problem though. Later on, you realize that in the real world, when it comes to parameters, you know which one you only have? The only one you may actually have is this one. Yeah, you don't have this and you don't have that. Okay? So in the first part, what happens is we might just give you the population standard deviation. But the problem is, in the real world, you don't have that. How am I supposed to know what the population standard deviation is, right? You don't have that unless you have the graph, right? So later on, what's going to happen is you're going to use this sampling distribution, sample standard deviation to estimate what? This one. Okay, buddy? All right. Waste of time? Almost done? How much time do I have left? 17 minutes. Okay, 70 minutes. Okay, ready? Okay, here we go. Okay, here are some conditions. Condition number 1, the sample you take must be a random sample. So it must be a simple random sample. So from now on, when you read a question, can you hunt this down? If you don't see that, you don't see SRS, it doesn't tell you it's a random sample, what you're gonna have to make is a statement saying that you will assume that is a simple random sample. Okay? And the reason why this is important is because if I were to look at average weight of high school students, here's my population. Okay? If someone goes, you know what? I want to show the world that, people in North America are obese or they're too heavy, then where would they take the sample if it was not an SRS? You would just take people over here and then you go, here's our average. Okay? That supports my point. On the other hand, if I want to complain about, hey, North American students are anorexic, they don't eat, then if I can just take any sample that's not random, where would I take them? In the far left. Okay? We don't get to eat here. Hungry as people in Africa. Okay? They eat nothing. Malnutrition. Okay? Food is too expensive. Inflation too high. Okay? And then you take from there. So therefore, when you take a sample, it must be what again? SRS. SRS means that you take from everything here, everybody all possible. Okay? Yes, Rhea. You can repeat the same individual, yes. But again, okay, theoretically, yes. Let's say you have 100 people. 100 choose 3, for example. You can change the same person for a different sample, right? But you don't want the exact same, like let's say ABC. You don't want the same people, right? It could be A, B, and D in one, and A, B, and E another one, okay? Just that for sampling distribution, it's all possible averages, okay? But when you take a sample, how many samples do you only take? 1 only, okay? Yes or no? Okay, so key thing is the sample you take must be a SRS, okay? And if you don't, a random sample prevents bias over or underrepresentation of any group, okay? That part important. If they don't have SRS written down, what do you do again? You make the statement saying that you will assume that it's a SRS. Because if it's not an SRS, that means all the calculations you made is. Remember this for your project too, okay? Last year, I failed one group saying, you know what, your sample is not an SRS. It's basically selective sampling. How can you justify that the distribution is normal? Oh, I don't know. Remember, garbage in, garbage. Number two, sample size must be the same size every single time. Okay, this is theoretical. Okay, sample size will affect the variation of the sampling distribution. That makes sense. Standard error gets bigger or smaller. No, it's smaller to a certain degree, depending on what your sample sizes are. Okay. Number three. Okay, depending on the population distribution or sample size, the distribution of sample means is normally distributed. Okay. Now from now on, write this down. The variation in the distribution sample mean is smaller than, okay, then whatever, okay. And then these two are repeats. They just repeat it, okay? This one, okay, this one, I'm gonna go back when you're ready, okay? Everybody good? Okay, first one. How do you know the sample distribution is normal? You ready? Here's the condition again. Population is normal. And then that means that sampling distribution be normal. Okay? If we told you population is normal, sample distribution automatically normal. Okay? If the population is not normal, it means it could be bimodal, skewed, uniform, or inverted, whatever it is, right? That means that your sample size must be 30 or more. Okay? If the sample size is big enough, then the sampling distribution will be normal. Okay? Does that make sense? Okay. Can you really check with your partner if they're actually focused? If they're not, can you hook them up? Okay. 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 Everybody good? Yeah. I'll look away. Yeah. Okay. If it helps. If it helps. This is for your own good. Okay. I care about you as a friend. I'm not abusing you. Okay. This is not violation. This is me supporting you as a friend, doing what it takes to see you successful. Okay. All right. Isabella, can you be a friend to Lydia? All right, move on. Okay. This slide is supposed to be a video. This video, important. I have 15 minutes left. You want to end the class watching this video? This video, okay, fine. You know what? Instead of me talking, okay, let's do this. BBC. Hi, I'm Mike Merritt. Today, we'll discuss the concept of a sampling distribution of the mean. In many fields of study, we collect data. These data are used to calculate an estimate, which we use to understand our world. Usually, we collect only one random sample and then use it to estimate something, say the mean of a much larger population. But what if we had collected another random sample? Wouldn't the mean be different? Wouldn't our estimate of the population mean change? So, how can we know that our one sample can be trusted to represent a much larger population? And how can we know that our work as statisticians is precise? The concept of a sampling distribution helps us to understand how we can use one sample to make statements about the mean of an entire population. A sampling distribution is an important concept in the statistical sciences. It's foundational, and it's crucial that you learn it. But what is it really? A sampling distribution is the probability distribution of a given statistic based on a random sample. It describes the what if of all the possible estimates we could have ended up with. Still not sure what I'm talking about? Stick with me. Today, to help us understand these concepts, we will be estimating the average length or mean length of fish that live in this lake. The thing we're interested in estimating today, which we will call a parameter, is the population mean. Our variable of interest is the length of a fish. We have a random sample of 25 fish from this lake here, and we will begin to measure the length of each individual fish. Now, in order to get the true population mean of all the fish in this lake, we'd have to measure every single fish. And that could be thousands. And we don't have that kind of time today. So today, I'm going to entrust the skills of a special friend of mine. Neptune, can you please help us calculate the length of every single fish in this lake? The important thing to learn here is that we must understand how samples behave when we know, well, everything, the truth. We can do this using probability theory. First, we're going to build up an understanding of how samples behave when we know the true values for the entire population. Then, we'll be able to learn how to use a sample to try and make statements about the entire population in the real world, when we don't actually know the truth without help from Neptune. We do this using statistical inference. So we now know the mean length and the standard deviation of the lengths. And this probability distribution shows the lengths of all fish in this lake, every single fish. So we know that this population has a mean length of 40 centimeters and a standard deviation of 10 centimeters. Thanks for your help, Neptune. We now know what we can do when we have the power of Neptune at our disposal. But what if we don't? What if we're back to being regular statisticians? What if we can't count each and every fish? We will now collect a random sample of 25 fish and measure their length and calculate the mean of the 25 length. We will call this our sample mean, or estimate of the population. It's important to remember that this sample mean is just one of many we could have gotten, just by chance. We would have a different sample mean each time we collect data because each set of fish is slightly different from one another. Look at this histogram. It's starting to show not 1, not 2, not 3, not 4, but all of the possible sample means we could have ended up with. Wouldn't it be great if we could see a histogram of all the possible sample means without having to collect sets of 25 fish over and over again forever? What would happen if we ended up with a different sample of 25 fish? You'll be pleased to hear that there is a way to know approximately what the shape of this distribution would look like without repeating the sampling process thousands of times. Thanks to Neptune, we now know that the true mean of fish in the lake is 40 centimeters and the standard deviation is 10 centimeters. And we know that the distribution of the lengths of all fish looks like this. Then what's going to happen is we're going to go out with our fishermen and we're going to take a random sample of 25 fish from this population. And when we take that sample of 25 fish, we expect our sample mean to be equal to 40 centimeters, the true population mean. Although we know that it's not going to be exactly equal to 40 due to what we call sampling variability. Now imagine all the thousands of random samples we could have taken. Each mean deviates slightly because not all samples have a mean that equals Neptune's true mean of 40. The standard deviation of all possible means is called the standard error, and we can work that out. The standard error is the standard deviation of the lengths of individual fish divided by the square root of the sample size. So our standard error is 2 centimeters. And this tells us typically how far the mean length of a sample of 25 fish deviates from the true mean. So typically, we're going to end up with a sample mean about 2 centimeters away from the true mean of 40. Even without Neptune, we have an idea of how close our estimate will be to the true value. The sampling distribution of the mean will be approximately normally distributed under certain conditions. In fact, an old rule of thumb tells us that approximately 95% of sample means we could get will stay within about 2 standard errors of the true mean and be between 36 and 44 centimeters. That's most of them. Not bad for a simple guy with only a paper cutout of a fisherman to help him out. Now, check this out. sampling distribution, the distribution of all the possible means we could get, is approximately normal or bell-shaped. Okay, so we think of the sample mean that we're going to get as one of many possible sample means we could get. And we can think of pulling it out of this distribution here. Even if this here, the population of all individual fish lengths is not normally distributed. Like in a different lake with an unusual proportion of large sea creatures. This here, the set of all possible means, would still be normal and bell-shaped, as long as our sample size is large. Now that's pretty cool. Now, you may be thinking to yourself, why is Mike spending so much time pretending and talking about what-ifs today? Well, the reason is that in everyday life, we generally don't know the true values for an entire population, and we must use a sample to try and make statements about the population we're sampling from. Learning how samples behave when we do know the true values for the entire population allows us to build the theory necessary to make statements about a population when we do not know the true values for the population. In the videos to follow, we will discuss how the sampling distribution of the mean can be used to help us make statements about a population, as we learn how to construct a confidence interval and test claims using hypothesis tests. Don't forget to check out the statistics visualizations that accompany this video. You can find the link in the description. Thanks for watching. Make sense? Sense? Okay.
Was every UBC lesson like that?
I don't think so. That'd be nice if it was. Okay, so how about this? I'll post an online quiz for 8.1, 8.2. Did I put one for chapter 7 yet? Did I put anything for chapter 7 yet? I did? Okay, so chapter 8.1, 8.2 online quiz, okay? Do when? Thursday or Friday?
Friday.
Thursday? No, Friday? Okay, fine. Friday, 9 p.m., okay? Sound good, everyone?
Friday.
Okay, enjoy the rest of your week. Yeah. Don't get stressed out and, whatever.